So I wanted to talk today about the point in physics where we can't explain things through the classical theory, so then we have quantum mechanics. And one of the things that ends up happening is you have this situation of Schrodinger's cat, right? But I don't want to go into Schrodinger's cat just yet. What I want to talk about is the issue comes up when you talk about the collapse of a wave function. So the collapse of the wave function is this concept in quantum mechanics that refers to the sudden change of a quantum system's probability distribution when it's being measured, right? It's almost like the point of measurement sort of changes what you previously have into something that's more concrete. It's very strange, right? And so according to the Copenhagen interpretation of quantum mechanics, before a measurement is made, a quantum system exists in this superposition of all possible states simultaneously. So you could have so many different outcomes that are possible, but you don't actually finalize which outcome it is until you actually go to measure it, which is kind of weird, right? Very strange how reality works in that way. So what they'll do is they'll talk about something called the superposition. The superposition means that the quantum system exists in the superposition of all possible states simultaneously, which is then being described by the wave function. But as soon as the measurement is performed, then the wave function collapses to a single state. And this corresponds to the outcome of the measurement. So at that point in time, it's like it's crystallized. It's no longer a cloud of these different possibilities. It's now just one particular measurement. So the superposition principle as a whole, or also known as a superposition property, states that for all linear systems, the net response caused by two or more things is the sum of the responses that would have been caused by each thing individually. All right, that's in general, rather than just applying it in the quantum mechanics situation. So when you talk about the wave function collapse, they kind of describe it in terms of mathematical projection postulate, which states that on measurement, the wave function collapse, right? You see in the image here, right, where you've got the wave function, and it's like a little mountain, right? Because, you know, when you're looking at a realm of probabilities, right, you're going to have like a probability distribution, which, you know, is like, you know, this sort of, what do you call it? It's kind of like a parabola, right? And, you know, but in this particular case, you actually have in 3 dimensions, which is why it looks like a mountain. So now the wave function is going to collapse to this eigenstate or eigenfunction of the whatever is being observed, right? Once it's measured, corresponding to the measured eigenvalue. In simpler terms, it means that the act of measurement forces the system into one of many possible states, and all other possibilities disappear. Just like that. It's like magic, right? In case you don't know what an eigenfunction is in mathematics, an eigenfunction of, let's say, like a linear operator like d, would be defined on some function in any non-zero function, which we'll call f, that in that space, when acted upon by d, is only multiplied by some scaling factor, which is called an eigenvalue. Some people might even call it an eigenvector, or an instance of an eigenvector. So as an equation, this condition will be written as, you know, capital D function f, right, equals lambda times the function f, right? And the solution to this equation, you know, might be subject to any boundary conditions that would limit the allowable eigenvalues and eigenfunctions. The equation itself is a form of a differential equation, right? And so a lot of people have a lot of disputes about how this all works, right? And just to make a refresher on linear differential equations, usually it takes a form like, say, like dy over dx, you know, plus py, which equal q. P and q are like these numeric constants. And the functions you're dealing with in that particular situation will be the functions in f. But it's really consists of a y, right? Because that's why you have py, right? P is acting like a, what do you want to call it? some sort of modifying value, right? If we were doing a linear equation, we would call that the slope, right? And you're also going to have like some sort of derivative of y along with that, right? Even if you wrote, say, d over dx, that's an operation that means take the derivative with respect to x. Because these are now partial derivatives we're talking about. We're not talking about full derivatives. We're talking about partial derivatives. So dy over dx indicates take the derivative of y, but with respect to x. So in other words, one of them is going to be held constant, and then the other one's the one you're actually going to take the derivative of, which is why it's called a partial derivative. So dy over dx would be like a gradient of a curve, right? Which is why we're dealing with something like this. It looks like a mountain. The d represents an infinitesimally small range, so that it's essentially as though you're doing these small, minute changes in y in x, as you would for, say, like a y equals mx plus c graph, but over a very small range. Because the idea is that you can approximate area, or in the case of 3D, volume, if you take these little small slices, like, you know, and you're adding them all together, and that will actually equal the actual area or volume you're looking for, right? Sometimes instead of representing it as just a regular small d, they'll represent it as a curly d, right? And that's a mathematical symbol that comes from, I believe, the Cyrillic alphabet. And so in calculus, we use that in place of the d, where you're dealing with functions with more than one variable, because, as I told you, we're dealing with a partial derivative here. So that means that instead of taking the whole derivative, as you would with d, the curly d says take the partial derivative. And the wave function itself is going to be called psi, and it's going to have like these two parameters. Well, one is going to be x, and the other is going to be t, right? It's basically like x is some sort of complex number, and then you're taking it at t, which is different points in time. So quantum superposition now is a fundamental principle of quantum mechanics that states that linear combinations of solutions to the Schrodinger equation are also solutions to the Schrodinger equation. This follows from the fact that the Schrodinger equation is a linear differential equation respect to time and position. So the state of a system is given by a linear combination of all the eigenfunctions of the Schrodinger equation governing that system. But remember, as I told you, when the collapse happens, that's the point of measurement. And at that point, all the possibilities disappear. You only just get the one outcome. And so the collapse of the wave function is something that has to be dealt with in quantum mechanics. And you know that the combination of these solutions can only resolve to one particular solution. They're all solutions, but at some point, only one of those solutions is what we're going to end up going with. And so because of that, once the collapse happens, then now it's like the system, the quantum system's probability distribution, right? Which I told you is like the little mountain. At that point, like I said, it just goes down to like a singular answer, a singular solution. And so this is something that's baffled people in quantum mechanics, because quantum mechanics, the principles and the methods that are used are very sound. They help where classical physics cannot help. But the problem is because of the fact that you can have all these multiple probabilities of position and a state, once it collapses, people are like, well, what does that mean? And that's where Schrodinger's cat comes in, right? Because Schrodinger comes along, I want to say in the early 1900s, and he's saying that, okay, you could have a box where on the one hand, the cat is dead in the box, and on the other hand, you open the box and the cat pops out alive and well. So you got these two possible situations that can happen, but you don't really know what's happening. Like, the cat is actually dead and alive at the same time, which makes no sense, right? So that means that, physicists are going to want to explain that. They're going to want to say, well, how can that be? How does that happen? How can a thing be in two places at the same time, or in two states at the same time? And so when you talk about that projection postulate, that says that, you know, upon measurement, it collapses to this particular eigenstate or eigenfunction. Um, that means the active measurement forces you into one of the possible states. That's it. Everything else disappears. And so physicists and other scientists have been debating for decades, what do you do in this situation? Some just accept it. Some just say, you know what? It is what it is. If there's many possibilities and those possibilities disappear when you go to measure it, so be it. You know, I want to say um, there's the guy who with the many worlds theory, Erwin Schrodinger, right? No. I'm sorry. I messed that up. Not Schrodinger. Hugh Everett III. So Hugh Everett III in 1957 says, well, you know what? The way it works is because, I don't want to screw this up. He's basically saying that all these different possibilities are their own universes, you know, right? So in other words, you have this many worlds theory where the wave function never really collapses, but instead the measurement you get is your timeline, right? Your timeline says that this is what's going to happen, and you're on that timeline. You can't get off that timeline. Everything continues on that particular timeline as far as you're concerned. But somewhere else, there's another you. And one of the other possibilities is what came out in that scenario. And then in another place, there's another you. And the third possibility comes out that. And so that's where now you get into all of the science fiction that we see nowadays, where everybody's always talking about, oh, I went to a parallel universe, parallel universe. Oh my God, we have to go back in time. You know, it's like, you know, now we created a branch because, you know, since this person was killed in this timeline, you know, we need to jump to another timeline where they're still alive or something, you know, and you get all these really wonky movies trying to use science to try to explain what's going on as a great storyline, but it's not necessarily always scientifically accurate what they're saying and what they're doing. But this is what came out of Everett in 1957 when he basically tried to explain it, because he says to himself, I just can't explain why you have all these possibilities, all these things that exist at once, but we only see one instance of it when we actually go to measure it. And so that's where the many worlds theory comes from. So when you think about Schrodinger's cat and the many worlds interpretation, some people think they're almost the same thing. Although I don't know if Schrodinger specifically said that in his lifetime. He probably alluded to it, right? That if the cat's alive and dead at the same time, then in essence you kind of have like two different universes, one where the cat's alive and another where the cat's dead. But really it's kind of Everett that really pioneered this idea of the many worlds theory. So this is what I wanted to talk to you about today, and I hope you enjoyed this discussion. I know a lot of it is pretty heavy, but this subject is very heavy, right? Quantum mechanics is not an easy subject, and this is just scratching the surface. So please continue to like, share, and subscribe. I appreciate your support. I love each and every one of you. Have a wonderful day. Take care.